Hello YouTube. I want to cover a very interesting subject today, but it consists of several themes. Of course, I'm speaking about possible intelligent life in outer space and our solar system, other than ours, of course. And I want to start by saying that ocean containing planets and satellites offer the greatest possibility of life in our solar system and beyond. This is my opinion based on years of research. I believe that the aquatic aliens, so to say, or underwater humanoids, whose encounters and visits I have investigated for decades, may actually be visitors from such ocean worlds in the outer space, and that such celestial bodies containing oceans may be just way stations on the way of the exploration of the outer space by an advanced civilization. You can see my videos on the subject of the underwater aliens from Lake Baikal and beyond. I also pointed out the interest of world and regional powers to Mariana Trench and urge you to pay attention to the scientific and military research in that part of the world, of course, to the extent that such news are disseminated. I personally update the subject in my videos. So let me start by telling you about a very interesting American research. But first, let's look at the world below the ocean surface, the world that is not typically observed, and the really fantastic life that exists there. Hydrothermal vents at the seafloor offer clues to the origins of life on our planet and beyond. Hydrothermal vents flow up through cracks at the bottom of the ocean, which, much like hot springs on land, spout the mineral-rich liquid that has been heated beneath the seafloor. Deep sea hydrothermal vents are found around the world, most often in volcanically active locations along the crest of the global mid-ocean ridge system. Magmatic activity driven by upwellings of heat in Earth's mantle causes the brittle tectonic plates that make up the Earth's outer shell or crust to split. As the plates spread, new seafloor rock is formed by magmatic activity and volcanic eruptions. This magmatic and tectonic activity creates cracks through which seawater percolates in crustal rocks, much like hot springs on land. Okay? Hydrothermal vents spout mineral-rich liquid that has been heated beneath the seafloor. Some things I want to repeat so you get a clearer picture. Well, officially it was first discovered in 1977, those hydrothermal vents, and were found to be populated by previously unknown organisms in quite a novel environment. According to a very interesting institution, the Woods Hole Oceanographic Institute, the largest independent oceanographic research institutions in the United States. This discoveries fundamentally changed our understandings of Earth and life on it. Please know that in some instances the Soviets and the Americans jointly conducted such research, but this was not being advertised, so to say. Hydrothermal vents are found around the world, and like I said, most often in volcanically active locations. And volcanic activity driven by upwellings of heat in Earth's mantle causes the brittle tectonic plates to split apart. It's in the outer shell. They split apart and spread apart. So the new seafloor rock is formed by volcanic eruptions. And again, this volcanic and tectonic activity creates cracks through which deep sea water seeps into the rocks. The water, which at the seafloor is 2 degrees Celsius, or about 35 degrees Fahrenheit, makes its way through the cracks towards the heat source called the magma chamber, which can sit about 1 to 2 kilometers about 3,000 to 6,000 feet below the sea level, seafloor. In some systems, the rocks surrounding the magma chamber is very hot and heats the water. The temperature of these fluids could exceed 400 degrees Celsius or 700 degrees Fahrenheit, which is more than 4 times the boiling point of water at Earth's surface. This is the life down there below. Few people see it. But one of those who does see it, the American scientist McDermott, she's a geochemist and field scientist who studies life at the seafloor. She is a chemical oceanographer and faculty member in Lehigh University Department of Earth and Environmental Science. McDermott collects and studies the liquid that shoots out of the volcanic parts of the deep sea, called hydrothermal vents. The vibrant animal and microbial communities that live at the seafloor offer a glimpse into a world that may hold clues to the beginning of life on Earth. According to her, hydrothermal vent ecosystems exist in permanent darkness. Understanding the chemical makeup of these unexplored waters offers a peek into how life survives without sunlight. So there is a light that doesn't depend on the sun. Such an understanding could illuminate the origins of life, or Earth and beyond. For example, in 2017, she researched the cold Arctic waters, and if you watch my videos on the subject, you will learn how much UFOs, aliens, espionage, warfare, and things we cannot even comprehend takes place there. Taking a trip to explore the Arctic seafloor has a lot in common with space travel, actually. It takes days to get there, only can be reached aboard a specialized vessel, and it's basically an unexplored frontier, one of the last ones. And yeah, to me, it's also an area of possible military confrontation. The West against Russia, or maybe the West, Russia, and China against a much more powerful adversary. I explained a lot about the Russian Arctic interest and areas in my book, Russia's USO Secrets, and of course you also can see my updated videos. You see, the Arctic environment may be similar to the surface of some moons. That is the reason that National Aeronautics and Space Administration, or lovingly known as NASA, has taken an interest in McDermott's work. Of course, the agency co-founded an expedition into a field location near the North Pole on board of Polarstern, a German icebreaker belonging to the Alfred Wegener Institute for Polar and Marine Research. An icebreaker is exactly what it sounds like, a highly specialized ship capable of breaking ice in order to move and navigate to the ice-covered waters, while McDermott was one of the over 40 scientists who made the trip, which began at a port in Tromsø, Norway. Their destination, a remote part of the Arctic called the Gakkel Ridge. And that's the Russian pronunciation. The Gakkel Ridge, located between Greenland and Siberia, was long believed to be non-volcanic. Researchers first found evidence of volcanic activity in 1999 and of hydrothermal vents in 2001. Until the team aboard Polarstern arrived, no one had explored the target area in 10 years. We're speaking about terrestrial beings, of course. McDermott was among a team of chemical and biological scientists there to explore and map the area, collect water samples emitted from the vents, and examine the novel geochemistry and microbial life contained therein. Multiple lines of evidence show that the team successfully obtained samples from within 200 meters of the deep seafloor vent source, closer than anyone is believed to have reached. They spent 7 weeks aboard the Polarstern, Once they reached the Arctic, the ship spent days breaking through ice as thick as 1.5 meters, about 5 feet, to reach their first destination. It is exactly this environment, a liquid water ocean overlaid by an icy shell, that makes the Arctic deep sea of interest to NASA. Over the past several years, NASA's Hubble Space Telescope imaged possible flumes of water vapors erupting off the surface of Europa, one of Jupiter's moons. That discovery has put Europa on a short list of bodies in the outer solar system that could support life. And I've done a video on that too, using Russian information too. And the Russians are no less sophisticated than the Americans in trying to find out what's in the Arctic waters. Well, during its first 13 years orbiting Saturn, Cassini captured a similar phenomenon at the south pole of Enceladus, one of Saturn's moons. Cassini data indicate that the geyser-like plumes may be from hydrothermal vents, and that energy sources for microbial life may exist on Enceladus. I suspect NASA knows more, but is too shy to reveal their knowledge. Same with the Russians, except for Sergei. The Russian scientist from the prestigious Mazhaysky Military Space Academy, space engineer, most likely former Russian space intelligence officer, who ruminated about Enceladus and life there on his website, and not that long ago. He's a good indicator, in my opinion, of where Russian science, albeit not entirely civilian, looks at. McDermott and NASA have a few questions in common about the hydrothermal vents, including what makes such an environment habitable, how much life is there, and what is it doing. According to McDermott, the seawater undergoes chemical reaction with the basaltic or ultramafic rock. At that point, the seawater has been transformed into a hydrothermal fluid. It is not seawater anymore. The chemical transformation process that occurs when ultramafic rock comes into contact with water is called serpentinization. Many scientists wonder whether serpentinizing hydrothermal systems played a role in spawning life on Earth. As the transformed water heats up beneath the seafloor, it becomes buoyant and is expelled back up like a spring, creating a flume of chemical soup. The time between volcanic eruptions varies widely depending on the system, with some systems erupting every decade, others every 10,000 years. However, even in the interim times between volcanic eruptions, submarine hydrothermal springs continue to flow through the sea floor rocks and cycle up to the seafloor. During the expedition, a remotely operated vehicle roamed the sea floor in tandem with towed sensors and water bottles, collecting samples that McDermott, on board of the Polar Stern vessel, would immediately examine for methane to gauge the vent location. The more methane detected, the closer they were to the vent origin. After the trip, the samples were transferred to the laboratory for further study. What was she looking for? McDermott said that we know that hydrothermal vents are permeated with life and that this life is dependent on chemistry. She was particularly interested in measuring the levels of methane and hydrogen, as this could potentially support life in the Arctic vent plume. When they're expelled at the seafloor, hydrothermal vent waters are enriched in methane and hydrogen, especially the very energy-rich free molecular hydrogen, which can serve as fuel for microbes. Interestingly, free hydrogen has been found in the plumes of liquid spouting from the Saturn's moon Enceladus. The fact that this life in the dark is among the most poorly understood on the planet is reason enough to study it, though there are others. These deep sea ecosystems have much to teach about how life is sustained below the reach of the sun's energy, both in our ancient oceans and in the modern day. Because deep sea water is not warmed by the sun, it remains at a consistent 2 to 4 degrees Celsius, 35.6 to 39.2 Fahrenheit. Relative to the shallow ocean, the deep sea is a stable environment, and on human timescales, it is largely immune to the impacts of extreme changes in climate that have affected and continue to affect the ocean closer to the surface. And I will add an excellent place for underwater bases. The vent fluid chemistry has profound effects on ocean water and offers a rare glimpse into microbial life that may have lived in places like this since the first oceans formed 3.8 billion years ago. The whole system is dependent on chemical energy rather than sunlight. At her Lehigh University lab, McDermott examined the samples for clues about the chemical energy that makes life possible. She is most interested in how the chemicals are being formed, biotically from living or once living materials, or abiotically in the absence of life. There is a lot of chemical potential in the vents to form organic molecules containing carbon and hydrogen, either abiotically or biotically through microbial activity, according to the American scientists. Are these molecules found in the absence of life? The transition between abiotic to biotic interests her the most. She wants to know which molecules are here because of the living material that was already present, and which, if any, developed from non-living materials. The answer to that question is the key point of her field, defining abiotic pathways to create organic molecules derived in the absence of the life. Such molecules, termed probiotic chemistry, are an important precursor step along the pathway to form the complicated molecules that make up living things. Has any evidence of such prebiotic molecules been found in hydrothermal vents on Earth or elsewhere? There is a strong evidence for the abiotic production of methane, hydrocarbons, and a simple organic acid in hydrothermal vents. But as far as more complex molecules, not yet. They're either absent in low abundance or have not yet been discovered. The hydrothermal vents at the Karasik seamount of the Gakkel Ridge are around 3,100 meters, more than 10,000 feet below the ocean surface. Well, in 2017 there was only one remotely operated vehicle capable of navigating ice-covered waters and sampling vents so far down. It was called the Nereid Under Ice. A highly specialized underwater robot, Woods Hole Oceanographic Institution's Nereid Under Ice, is built to travel up to 40 kilometers, 25 miles laterally underwater, while still receiving control signals and transmitting data, including high-definition video, back to operators located on a ship via a hair-thin fiber optic tether. The vehicle can dive up to 2,000 meters, 6,500 feet beneath the surface to sample or survey the ice-water interface, the midwater or the seafloor. I believe in 2016, Arctic trip was the second successful expedition that the deep sea submarine to the Arctic seafloor had conducted. Well, McDermott is among the first to sample and study the plumes from the hydrothermal vents at the Gakkel Ridge. In a paper of preparation on the first results of the project, McDermott reported that the Gakkel Ridge vent fluid chemistries share commonalities with the Lost City hydrothermal field in the mid-Atlantic ridge and the Von Dam vent field at the mid-Cayman rise, revealing a new ice-covered ecosystem that's ripe for the study of life and other processes driven by abiotic production of methane and hydrogen by serpentinization. Her team's analysis of vent fluids revealed evidence for high-temperature, hydrogen-rich, likely ultramafic influenced seafloor venting. The team also observed abundant active microbial populations in the samples. Through analysis, and will be able to predict the nature of the vent fluid source, as well as identify the fate of the fluid as it gets dispersed into the surrounding ocean and overlying ice. Well, again, among the most compelling results she had found at that time, the samples closest to the source contain an equivalent amount of methane and hydrogen, and which implies that the hydrogen supplies from the abiotic vent fluid source exceeds the rate of drawdown by microorganisms in the plume, at least initially. How long does it take for this hydrogen to be consumed by microbes, and how far away from the source can it get, she asked. These questions, I guess, can now be added to the myriad others about these systems. I'm sure there are other questions we don't know about, and she doesn't, I don't think she knows too, but there are others who are interested in such research. Anyway, in 2022 we learned that the off-axis high temperature hydrothermal field was discovered at the East Pacific Rise. Spearheaded by the McDermott lab at Lehigh, the research demonstrates that there are more hydrothermal vents in the sea, deep sea, than previously thought, and underscores a need for bathymetric mapping to locate them. Finding a new high-temperature, off-axis hydrothermal vent field on the floor of the Pacific Ocean at 2,550 meters depth could change scientists' understanding of the impact that such ocean floor vent systems have on life and chemistry of Earth oceans. So, the team of researchers, including McDermott, she's a chemical oceanographer and faculty member of the Lehigh Department of Earth and Environmental Sciences. They discovered an off-axis hydrothermal field named YBW Sentry in the area of the global mid-ocean ridge known as this Pacific Rise. Very important area, very important. The study area is about 200 miles off the coast of western Mexico. The new vent site covers an area equivalent to a football field, roughly twice the size of the nearest active hydrothermal vents in the region. The chimneys resemble candelabras that are the height of a 3-story building. The findings have been published in an article in the Proceedings of the National Academy of Sciences. Outside of that, I'd like you to keep your eyes open on reports from Mexico about UFO activity. I would say about the same area of the coast of western Mexico. You can find it if you do your own research. Now, her research led to the discovery of the off-axis vent field along the East Pacific Rise. And the team that she was with collects fluids from the black smoker chimneys and analyzes them for their geochemical characteristics, which can indicate the temperatures at which the fluids are forming. Hotter temperatures could be a sign of an impending eruption. At the same time, the team also instruments, so the active vent chimneys with self-recording fluid temperature loggers to provide measurements every 10 minutes over 2-year time periods. The temperature measurements provide a time series of the changes the vents experience. The research team has 9 vents instrumented in the study area. Near bottom bathymetric surveys conducted by the research team between 2018 and 2021 with the anonymous underwater vehicle Sentry provided by the Woods Hole Oceanographic Institutions. This is how they did research this time. And of course the institution again provided an advanced underwater vehicle. The 3-year research project is funded by the United States National Science Foundation's Ocean Sciences Division, Marine Geology and Geophysics program. And according to McDermott, there is much still left to be discovered about the deep sea vents along the global mid-ocean ridge, both in terms of where they are located as well as their geological, geochemical, and biological characteristics. While she hopes their study will motivate future research efforts to target mapping those off-axis area along the global mid-ocean ridge crest to better quantify the extent of an off-axis versus an on-axis hydrothermal venting. Now, let's go to outer space. Let's look at what Sergei thinks about Enceladus. Could extraterrestrial life have originated on Enceladus? Is what he asked recently. Enceladus, Saturn's moon, is one of the most interesting worlds in the solar system. This cosmic body is very remarkable in its profile. These are hundreds of geysers emanating from the southern polar region of the satellite. Along with Europa and Mars, Enceladus is a priority target for exploration. Why? Because of the existence of a subsurface ocean in which life could appear, or I will add, already exists, and it may be an intelligent life as well, sentient life. But how likely is it that it could have originated on this tiny satellite? And isn't Earth life a descendant of the life that originally appeared on Enceladus? Asks Sergei. How did life on Earth come about? No one knows if there are any life forms on Enceladus, although nothing prevents scientists from speculating about the conditions of its appearance. The origin of life on Earth is a very difficult question, but most researchers agree that the so-called serpentinization, which I mentioned before, played a fundamental role in its appearance. This is a chemical process, as a result of which the properties of some rocks change when they come into contact with water. Serpentinization in hydrothermal vents associated with volcanic activity is one of the favorite mechanisms for representing the ideal environment for the emergence of life on early Earth. Although far from the only one, of course. Today, terrestrial hydrothermal vents are concentrated mainly in oceanic ridges, as we already know. That is, in areas of separation of tectonic plates. Currently, these areas extend approximately 80,000 kilometers in length. Although not all of this extended area can be found, active sources can be found there. When the Earth was very young, from 4.56 billion to 3.8 billion years ago, hydrothermal activity on our planet was higher than it is today. But it is obvious that only a small fraction of the Earth's crust could undergo serpentinization processes, since most of the Earth's rocks did not come into contact with the waters of the oceans. However, Enceladus is a different case. This satellite, which has a diameter of about 500 kilometers, consists of an outer crust of ice and a core, which consists of rocks with a strong presence of water. The modern degree of differentiation of Enceladus' interior is unknown to science, but it is clear that shortly after its formation, the core was a homogeneous mixture of rocks and water. Because of its small size, the center of Enceladus has never been subjected to enormous pressure. Therefore, it is possible that it was completely permeable to liquids and gases. In other words, the serpentinization process on Enceladus was not limited to hydrothermal vents in the oceans as on Earth. It could cover the entire satellite, almost from the surface to the very center. Consequently, the mass of rocks subjected to serpentinization on Enceladus would be even greater, and we're talking in absolute terms, than on Earth. Considering that the presence of hydrothermal vents on the ocean floor of Enceladus has been confirmed relatively recently, everything indicates that this geological process also took place in the past. However, serpentinization by itself does not contribute to the emergence of life, especially the temperature or pressure is excessive. But again, Enceladus has never had this problem. At the center of the satellite, the pressure is about 24 million pascals. This is about the same as at a depth of only 2,300 meters in the Earth oceans. As for the temperature, the absence of a large number of radioactive isotopes prevented the heating of the interior of Enceladus to levels incompatible with life. So we can draw this conclusion. During the first few 100 million years after the formation of the solar system, the bowels of this small satellite could be a more favorable place for the emergence of life than on Earth itself. Not only that, in addition to rocks, water and heat, Enceladus has a significant amount of organic matter. And so, there are all the ingredients and conditions necessary for the emergence of microscopic life forms. But what is even more interesting is that Enceladus has a unique transport mechanisms connecting the underground ocean directly with outer space. Of course, we're talking about the famous geysers of the South Pole. More than 100 active jets throw out particles consisting of ice, salts, and organic substances. Most of these particles form an E-ring around Saturn, but many of them eventually disperse across the planet's satellite system, including Titan, and some even fly away and disperse in the solar system. And here is an interesting question arises. Do they reach our planet? Yes, the probability that particles from the bowels of Enceladus will reach the planets of the Earth group is very small, but it is not equal to zero at all. If we take into account the Poynting-Robertson effect, a small particle, about 10 microns, located at the distance of Saturn from the Sun, about 1.5 billion kilometers, would take about 650,000 years to reach the Earth orbit, perhaps even less, if we are talking about larger particles, because in this case, other forces would already come into action, such for example as the Yarkovsky effect. And finally, one more fact: the small size of the particles would allow them to survive, getting into the Earth's atmosphere without collapsing at the same time. It is quite obvious that the high habitability potential combined with the small size made Enceladus a unique possible source of life for the entire young solar system. Yes, perhaps other worlds were more favorable for the appearance of life, but none of them had a mechanism capable of throwing its seeds directly into space with such ease. Until now, the only phenomenon that panspermia could use to exchange life forms between worlds were large impacts of comets and asteroids on the surface of planets. But Enceladus pointed us to another possible path. Enceladus may be or could be a natural distributor of microorganisms, an example of the fact that life does not need human beings with a space program to spread through outer space. Of course, it is very likely that life on Enceladus never originated. After all, many theories suggest that its ocean is a transient phenomenon and not permanent at all. On the other hand, Perhaps early Enceladus was such a favorable place to live, as some scientists suggest. Maybe. But we won't know for sure until we get to explore that celestial body in detail. In addition, let's not forget that the particles of the Enceladus ocean scattered not only across the solar system. Yes, some of them fall into the inner solar system. However, some eventually leave the realm of the sun and they go out into interstellar space. The possibility that particles from Enceladus with microorganisms inside them are wandering somewhere in the galaxy is certainly fascinating. But if we take into account that the surroundings of the galaxy should be full of worlds like Enceladus, then the possibilities look much more exciting. And if there's intelligent life in those oceans, it will want to reach out and explore the outer space. Look, it's possible that here in our solar system and now there are particles from another, not our analog Enceladus. Who knows where it's from? And who knows how many of them may be carriers of alien life forms. So, we can see that scientists in Russia and the United States are really interested in the hydrothermal vents and Enceladus. And please don't discount China by any means. Saturn's moon Enceladus is very small, but it may hold clues to one of the biggest mysteries of all time. Are we alone? Beneath the icy crust lies a global salty ocean, not too different from the Earth's oceans. Could that ocean contain life of some kind, an advanced life? This is a question that many scientists and the public alike would like to find an answer for. Enceladus, however, is very far away and planetary missions are expensive. But there may be an ideal solution, or at least it existed a short time ago. Billionaire entrepreneur and physicist Yuri Milner, originally from the Soviet Union and Russia, wants to, at least he wanted to send a private mission back to this intriguing world, and NASA wanted to help him. This incredible idea was first reported in New Scientist in November of 2018. Yuri Milner is a technology investor and science philanthropist. He was born in 1961 and named after Yuri Gagarin, the Soviet cosmonaut who had earlier that year became the first human in space. In July 2015, together with Stephen Hawking, Yuri Milner announced the launch of the 100 million Breakthrough Listen initiative to reinvigorate the search for extraterrestrial intelligence in the universe. And in April 2016, they launched Breakthrough Starshot, a $100 million research and engineering program seeking to develop a technology for interstellar flight travel. These philanthropic projects were founded by the Breakthrough Foundation, which Julia and Yuri Milner established. So I think we should stay tuned because we may be finding more about that satellite of Saturn and life there. And hydrothermal vents, please keep attention. And again, I want to underscore Mariana Strange. And the Arctic is always fascinating, and you can find much more about the Arctic in the playlists in my channel. Please help my research if you can. You will find the links on how to do it in the description to this video, and please tell others. And if you can, like my video and sign up for my channel, and so to say, and I'll bring you more interesting videos soon. Thank you.